Devontae Baxter comes to us from the University of California, San Diego, in the shadow of Mount Palomar. What else? We've got a PhD in 2023 from UC Irvine, and is now on his first postdoc, and it's a dual postdoc. He is an NSF postdoctoral fellow, but also a UC Chancellor's postdoctoral fellow there at UC San Diego. Thank you so much for coming. We're excited to hear about galaxy evolution. But before I do that, he also directs a computational astrophysics research preparation program that helps transition community college students from a 2-year school to a 4-year school there in the San Diego area. So he does many other things, including skateboarding. That he can tell you about that if he wants to. And the other thing is some of us are meeting for lunch, and that we'll meet up at, let's say, 120 at the basement floor near the elevators. And then we'll walk to Zoe's from there. Okay, with that, let's welcome Devontae.
Thank you so much for the kind introduction, Guy. And thank you all for coming today and having me at your beautiful campus. It's always a pleasure to be able to travel and share my work and what I do. So I'm always grateful to share with others. So the theme of today's talk is a theme that's central to my research, which is the physics that drives galaxy evolution in extreme environments. Now, when I say extreme, I'm referring to the most underdense and overdense regions of the cosmic web, which is visualized behind me. That's amazing visualization. So let's take a moment to appreciate what we're looking at. So here at the tip of this map is the Earth. And every single point represents a galaxy observed in the first year of the Dark Energy Spectroscopic Instrument Survey. Now, what's remarkable about this plot is that it includes the distribution of 600,000 galaxies across 11 billion years of cosmic time. Now, the key takeaway from this is that the distributions of galaxies isn't uniformly distributed throughout the cosmos. In fact, it's quite non-uniform. Now, that's something that human populations and galaxy populations have in common. Human populations on Earth are non-uniform. Same thing for galaxies. You can see this here. This map of the continental United States, the population density supplemented by the counties in which folks live in. And you can see this here again from this slice of the cosmic web. There are regions of extreme underdensity and extreme overdensity. And we know, as humans, these regions of underdensity and overdensity look extremely different. For example, if we look at Esmeralda County, Nevada, one of the least populous counties in the United States, looks very different from, let's say, Fulton County, Georgia, where I was born. Now, not only do they look different, but where you live on this map has a large impact on your life. It can impact things such as your career opportunities, your educational opportunities, your health and access to health care, and even your overall prosperity. Now, again, galaxies live in a variety of environments, going from very underdense and overdense regions. Now, these regions have names. So again, this is the slice of the cosmic web. All this data has been taken at Kennedy National Observatory. And the most underdense regions of the cosmic web are known as cosmic voids. These are regions with very few galaxies. Step up from that, you find filaments. These are extended threads connecting different regions of the cosmic web. And within these filaments, you can find galaxy groups, collections of a few to dozens of galaxies, all gravitationally bound, and they represent the most common galaxy overdensity in the cosmos. But they're not the most extreme. The most extreme galaxy overdensities occur in locations known as nodes, regions where the filaments of the cosmic web intersect. And these are the birthplace of galaxy clusters, most massive collapsed structures in the universe, housing hundreds to 1,000 galaxies, all gravitationally bound to a single structure. Now, following this analogy between human populations and galaxy populations, galaxies are also profoundly impacted by the environment. It can impact things such as their morphology. Are they a spiral galaxy or more elliptical galaxy? It can impact their gas content. You have a lot of gas, very little gas. And also their star formation activity. Are they wildly producing stars or has star formation dwindled down? Now, the focus on this talk will be some of my work trying to understand the role that environment plays in impacting star formation activity in galaxies. So to really appreciate this point, I want to explain what are star-forming galaxies in just very general terms. In very general terms, a star-forming galaxy is a self-regulated cosmic factory that takes in raw materials from its environment, being that cold atomic hydrogen, and it converts it into stars. And this happens through a process known as the baryon cycle, as illustrated here, but let's break this down into its key components. The first component has to do with inflow of gas. Gas inflow comes in from the intergalactic medium, and it funnels in onto the interstellar medium of the galaxy. To the second phase, known as gas consumption. Gas gets consumed and produces stars. These stars, they live, they die, they eject energy, momentum into ISM, and some of that gas gets expelled, becomes part of the circumgalactic medium, the CGM, other escapes. Now, a galaxy that goes through this cycle of inflow, gas consumption, outflow, inflow, consumption, outflow, fall on what's known as the star forming sequence. If you look at the rate at which a galaxy is forming stars, star formation rate, as a function of its existing stellar mass, or the number of stars in the galaxy, you find this fairly tight relation. This is known as the star forming sequence. Now, I've likened galaxies to factories, and similar to their terrestrial counterparts, they eventually, occasionally, permanently shut down production. And for galaxies, this process is known as quenching. It's when they fall away from the star forming main sequence, and they become this new subpopulation of quenched galaxies. Now, this gives rise to really cool distributions of galaxies in the cosmos. So this plot here shows the specific star formation rate, this star formation rate by stellar mass as a function of stellar mass. And you see there's a clear bimodal population here of star forming galaxies and quenched galaxies. And an outstanding question is understanding what is the genesis of this distribution? What caused this bimodal population of galaxies? Well, we know that environment plays a role. So this plot here shows the fraction of star-forming galaxies as a function of galaxy density. Again, going from the low density environments and voids, filaments, groups, to the most extreme overdensity being galaxy clusters. And as you march from low density to high density environments, you find less and less and less star-forming galaxies. In other words, quenched galaxies are more common in dense environments. Now, I went over this introduction just to motivate a few questions that drive or have driven some of my previous research. The main would be, what are the physical mechanisms that shut down star formation in galaxies in overdense regions of the cosmos? How does this depend on cosmic time? How does it depend on the stellar mass of the galaxies that you're observing? And how does it vary between galaxies that are members of groups versus the more massive galaxy clusters? And these are relevant questions because our current models, while they are amazing at reproducing a lot of observational results, tend to struggle when it comes to reproducing observations for galaxies that are quenched. So as an example, this plot shows the quench fraction as a function of stellar mass, where the markers show observations and the lines are predictions from this model. This is a semi-analytic model. First, I'll highlight the central galaxies. So these are all the galaxies. They're not in an overdense region. They're not being influenced by another galaxy. And our models do fairly well. We see a line at reproducing the overall thread of what's observed. But if you look at the satellite galaxies, now these are the galaxies that live in galaxy groups or clusters. The model grossly overpredicts what's observed. You can see here, especially at low masses. We observe this trend with stellar mass. As you go to lower stellar mass, you find a lower quench fraction. But this model has this kind of flat quench fraction. They're over quenching the satellites in the model. The same thing can be said if you look at hydrodynamical models. So this is some co-author work that I did a couple years ago or a year ago. So the black points are the data. All these bands are the observations from different simulations. And the key point here is that these models struggle to reproduce the physics of environmental. Okay, so I said the models are struggling. How do we improve the models? How do we get a better idea of what physical mechanisms could potentially be quenching these galaxies? Well, to do that, let's go to the drawing board and ask, how do you quench a galaxy? And there's been a lot of work in this field. And I think one of the key studies come from Peng et al. 2010 that looked at the distribution of galaxies in the Sloan Digital Sky Survey as a function of environment, stellar mass, and quench fraction. So from this plot, you can see two takeaways. First one being, if you look at low density here, but you change the stellar mass, you see that you get more quenched galaxies at higher stellar masses. This leads to this one pathway for quenching known as self-quenching or mass quenching. And it's thought to be due to internal processes in a galaxy. Think about star formation activity, black hole activity, etc. Now, if you look at fixed stellar mass, but you change the density, you find as you go to higher and higher densities, as I showed earlier, you find more and more galaxies that are non-star forming, quenched galaxies. This is likely due to environmental mechanisms. So we call this environmental quenching. So these are the two pathways that we think that galaxies are able to shut down star formation.
So can I just interrupt a little bit? You mentioned that the quenched galaxies have a very low mass, if I understood that plot correctly, but the high mass galaxies are the ones that become quenched. Is that correct? Or?
In the last figure, yeah. So in isolation, low mass galaxies tend to be star forming, but high mass galaxies can quench regardless.
And when they quench, they over time become a smaller mass, because I thought I saw a plot where you had a.
The mass stays constant.
It stays constant.
Yeah, the mass doesn't change. They don't.
Okay.
They don't.
Thank you.
So as an example of some internal quenching process, it could be due to outflow or gas ejection. So imagine you have this star forming galaxy. The blue here is the full component of the interstellar medium. The purple is the circumgalactic medium, or this high halo. So you have a galaxy, and with time, it goes to this episode of intense starburst or AGN activity, where it starts to blow out and heat up the gas within the galaxy. With time, if this is sustained, the galaxy can quench on its own. So that's an example of an internal quenching mechanism. Now, I want to go over the kind of a special case of environmental quenching, which I like to call global environmental quenching. This happened during the epoch of reionization. And this was the time, this last major phase transition in the cosmos, where the universe transitioned from neutral hydrogen to ionized hydrogen. And the cause of this was the first stars and galaxies turned on. They created this UV background that photoionized the gas, low density gas, some of the lowest mass galaxies, increasing the cooling time and preventing these galaxies from forming stars. So we think this is a mechanism that happens to the lowest mass galaxies in the universe. Now, if you look at general environmental quenching mechanisms, which depend on if a galaxy is in an overdense region in the cosmos, there's a couple ways to quench. I'm going to break down two categories. The first one is stripping or gas removal. An example of this would be random pressure stripping. So again, back to this cartoon, you have a star-forming galaxy. You're assuming that it's not in an overdense region. It's forming stars, falls onto a host system, and it begins to experience new physics. It begins to experience this pressure known as Frank pressure, which is proportional to the density of the gas in this overdense region, as well as the velocity of the galaxy itself relative to this gas. But it can resist this pressure. This pressure acts to remove the cold gas component in the interstellar medium from the outside in. But based on its surface gas density, mass profile, it can resist this and prevent it from quenching or being stripped. However, if Frank pressure exceeds this restoring pressure, the galaxy begins to have its gas stripped from the outside in, and eventually it quenches on fairly fast times. Another example, imagine you have a galaxy, it's able to resist the stripping, but it can still quench just by being within its overdense region. again, with this cartoon, we have a star from a galaxy, it falls onto the host system. Say that Brand pressure isn't able to remove the cold gas component, but it can strip away the CGM component, this hot gas halo. But due to the extremely hot temperatures over 1,000,000 Kelvin within these overdense regions, it can prevent gas, new gas, from accreting onto the galaxy. So once it's in this overdense region, it can prevent gas accretion. So with time, it will eventually shut down star formation just by consuming the remaining gas reservoir. And this is known as starvation. This part of kind of having the gas removed strangely. Very violent terms, but that's the literature. Now, I kind of go over this just to emphasize that these are about to quench on characteristically different timescales. For the first one, this stripping should go as the dynamical time of the group of cluster you're looking at, which goes as the rate velocity of the system. Whereas depletion, the depletion timescale goes on timescales that are proportional to the total gas that is within the galaxy and the star formation rate of the galaxy. Now, so if you can infer the quenching timescales from observations, you can kind of use this information to kind of disentangle what mechanism is potentially dominant in quenching the observed satellites. So I want to go to an example of how exactly I'm going to do that. So this is the Coma cluster. It's the most massive cluster in the nearby universe. It's quite remarkable. And I mentioned over this region, groups and clusters, they are permeated by this hot gas. And clusters is known as the intercluster medium, temperature between 10 to the 7 to the 8 Kelvin. And that's one way that we actually find clusters in the universe. They emit an X-ray through thermal electron radiation. You can use this X-ray temperature to infer the mass and size of the cluster. And if you have this information, you can kind of define a boundary, like what is your cluster? And then if you have observations, spectroscopy, photometry, you can determine membership, star formation rates, stellar masses, etc., which allows you to compute this quantity that I mentioned before, the satellite quench fraction. Right, but that's not the entire picture. Right, we want timescales, and that's difficult. That's very difficult because when we do these observations, we're looking at snapshots of the universe, so we can't perform these longitudinal studies. We have to wait a very long time. But what we can do is find analogs of our observed clusters or groups within simulations in terms of the redshift that we're looking at, the mass, the richness, the number of members. And then we can follow their infall histories with time. Follow the members that we observed at the snapshot and find when these members became part of the overdense region. So that's one way to kind of get around this. And then you can create a very straightforward model that you can use to estimate quenching timescale. So this model is parameterized by something known as tau quench. It's the time that it takes a galaxy to shut down star formation after entering the overdense region. So in this example, we have a star from a galaxy here. It's entering an overdense region, and it quenches on a timescale of 1 gigayear. So 1 gigayear after falling in, and then kind of the output of this, it generates a quench fraction, which is something that we can observe. You can imagine doing this with the same kind of infall history, but just changing this tau quench parameter slightly. Now, instead of 1 gigayear, it's 1.5 gigayears. And the outcome of this is that you get a lower quench fraction. So that's the basis of this model that I'm going to talk about in order to get that you can use to get environmental quenching timescales. Now, this has been done pretty extensively in the nearby universe. So I'm talking about the local group, which consists of the Milky Way and M31, Andromeda, our nearby neighbor. And also for galaxies and clusters and groups and the local universe. Let's say it's less than 0.05. And this plot shows the satellite quench timescale as a function of satellite stellar mass. I'm going to go through some results from the literature of using kind of this technique. So timescales that have been estimated for these very low mass galaxies, these are known as the ultra faint dwarf galaxies, are consistent with them quenching during the epoch of reionization. So before everything is global environmental quenching. If you go to slightly more massive galaxies, the timescales that they find are consistent with quenching to be a stripping. These are the classical dwarf galaxies. And these are galaxies within the Milky Way and Andromeda. Now, if you go to more massive galaxies, the timescales that they found are consistent with the depletion timescale that's expected for galaxies at this epoch. So, quenching timescales depend on stellar mass. Galaxies quench differently depending on their stellar mass range. Where these less massive galaxies quench through stripping, and these more massive galaxies quench more passively through starvation. And that kind of led to a question that I had regarding these massive galaxies. So this is in a very nearby universe, but does this picture hold if you look at galaxies in groups and clusters beyond the nearby universe? And that's the motivation for this project I'm going to talk to you about. So for our sample, we use clusters from the Go Green survey. This is the Gemini observations of galaxies in rich early environments. This was a survey done using the Gemini telescopes in Hawaii to explore galaxy groups and clusters. Overall, these are the sample for 26 groups and clusters between a redshift of 0.8 and 1.5. And the survey obtained a total of around 2,200 reliable spectroscopic redshifts, so we know how far they are from us. We can determine membership using this. It also includes deep multi-wavelength photometry spanning the full optical to infrared, so we can characterize these galaxies in terms of their stellar mass, star formation rates, etc. And kind of the takeaway from this is that it's the largest and most comprehensive galaxy cluster survey at this redshift. It's about 7 to 8 billion years ago. Just kind of going through the sample again, we take a cluster, this SBT CL0546. So all the green circles are the cluster members that we found, the red circles are the non-members. And for each galaxy, we get multi-wavelength photometry and residing optical spectroscopy to get these key parameters that we're interested in terms of galaxies. The sample that I used for my study included 14 clusters with around 1,100 satellite galaxies with stellar masses greater than 10 to the 10. So again, from this high mass regime. And these are some of the quench fraction trends that I observed. From left to right, we have satellite quench fraction of a bunch of stellar mass. It increases with stellar mass, which has been sound. It decreases with Hostage radius. So if you get further away from the center of the cluster, you find more star forming galaxies. Yes.
Are you already accounting for systematics here? Like maybe quenched galaxies would be more difficult to spot.
I'm sorry.
Like, are you accounting for systematics observations? Like quenched galaxies may be more difficult to spot because for that.
Right. Yeah. So that 10 to the 10 limit is because quench galaxies are harder to find than star forming galaxies, right? So we can find star forming galaxies below this 10 to the 10. So this is our stellar mass completeness limit essentially. If that's the question that you're asking,
Yeah.
right? So it decreases with host-centric radius, and it's fairly constant with redshift. Now for our kind of simulated sample, we found 56 clusters that are redshift max to our observed sample. So these are the analogs that we use from simulations. And the main point from this is that we can get infall history. So this shows you fraction of the cluster population assembled with a function of a look back time for these different kind of snapshots that we take on these clusters. So we know how the cluster population was assembled with time. And this is important because the model relies on this information. So TNG 300 is a simulation we use that provides this T infall, which we get from here, and T observation, which is based off the snapshot that we take the clusters from. Such that the maximum time for a satellite galaxy to environmentally quench is given by T max, T infall less than T observed. Therefore, the environmental quenching condition is such that tau quench is less than equal to T max. Where T max is fixed, but tau quench is something that we can vary within our model. So another cool thing that we did in this project is that many times folks have assumed that all the galaxies fallen in are star forming. We know this isn't the case. If you look at the fraction of the global quench fraction as a function of redshift and stellar mass, you find that there are more galaxies that are quenched, that are massive, regardless of environment, compared to the less massive ones. So we use this information to statistically determine or classify which galaxies would become in quenched versus which ones would become in star forming. As you can imagine, the more massive galaxies were likely to come in quenched. Okay, so just kind of going through the results for the model. So again, these are the quench fraction results of function of stellar mass. We account for the population of galaxies, the galaxies that came in self-quenched or quenched independently of environment. So then you can assume various quenching timescales, which are shown here, going from 0 to 3 gigayears, and these are constant quenching timescales. And one of the things that we notice is that these constant quenching timescales are unable to reproduce the observed quench fractions. The closest to that come to observations are this 1.2 gigayear quenching timescale, which overestimates at low masses, whereas this 1.5 gigayear timescale tends to underestimate high masses. So our interpretation of this is that the quenching timescale should have some mass dependence. So you can reparameterize tau quench now as some function that goes with the stellar mass. And if you do that, you can actually get some results that are more consistent with observations. You can do a kind of Bayesian approach to find which of these model parameters are most consistent with observations. So we do that, and we do a good job of reproducing the result as a function of stellar mass. But we also reproduce the result fairly well against closest radius and redshift. So we're doing something with a simple model that the semi-analytic models and hydrodynamic models aren't able to reproduce. We're able to reproduce quench fractions that are observed. And from this, we get a quenching timescale, which is kind of the key point. We find that the quenching timescale that's most consistent with observations looks like this. It decreases with stellar mass. And if you overplot the empirically derived total gas depletion timescale, you find that it's fairly consistent. So the interpretation from this is that perhaps starvation is the dominant quenching mechanism for massive galaxies and clusters, as you have one similar to what's been observed at 0. We were also able to look at this redshift dependence of quenching in clusters. So these are all clusters at a variety of redshift from redshift 0 to about 1.5. And we found that if you overplot the, well, for one, we find that the quenching timescales in the nearby universe are much higher than what's observed at earlier times. But we find that this is consistent with the redshift evolution of the total full gas depletion timescale. So interpretations for this, one is that starvation is the primary quenching mechanism for massive galaxies at Z of less than 1. And that starvation-driven quenching becomes less efficient at lower redshifts as global starvation rates and gas fractions decrease. So there are more gas, higher starvation rates at earlier times. These things can push through via starvation much faster versus galaxies that we observe today. Just a plot of the global starvation rate density over time. You see it peaks and it goes down. It's around 0.2. Okay, so that was the kind of first part of looking at clusters. I want to talk to you about some work that I've done with groups, which is quite similar. So this is one of the most famous galaxy groups, Stefan's quintet. And while it's quintet, there's only 4 galaxies that are a member of this group. Would anyone like to guess which galaxy is the interloper, the imposter?
NGC 7317. 7320.
7320, yes, you got it. So 7320 is the interloper in this system. I showed the JWST at the last time I gave the JWST image, and it's harder to tell. Just you can with this image, you can see that this one's clearly a blue spiral galaxy. So groups are cool. They are by definition gravitationally bound collections of a few to several dozen galaxies. In terms of mass, their range goes between 10 to the 12 and 2 to the 14 in halo mass. But why do we care about groups? I already talked about clusters. I said these are the most extreme environments in the cosmos. Well, as I mentioned before, galaxy groups are the most common galaxy overdensities. So to gain a complete picture, understanding of how an environment drives environmental quenching, we must study galaxy groups over a wide range of stellar masses and redshifts. But there's a challenge to studying galaxy groups. Groups are relatively galaxy poor. They have tens versus hundreds of galaxies, which makes them less efficient to observe. And it makes them more difficult to characterize. They don't all have this X-ray emitting or intergroup medium, which is one way that we detect clusters. But they're interesting, and I particularly want to probe a specific parameter space in this plot. So this is similar to what I showed before for galaxy clusters. Now this is for galaxy groups. It shows all the results, some of the results from the literature. The filled in markers are kind of the more massive satellites from 10 to 10.5 solar masses, or these unfilled markers are the less massive satellites. So in particular, I want to explore this region here around 0.8 in this space, and also wanted to look at these lower mass satellites around 10 to the 9.5 in solar masses. So the results here are based on group membership using less reliable photometric redshifts. So in grad school, this is some data that I had left over. We did observations of this really cool region of the sky known as the extended growth strip. You squint, you can see it right here. It's nearby Ursa Major. But you can expand this, and this is known as a legacy field. It's a field that's been observed by a variety of telescopes. It has this multi-wavelength observations. Many spectroscopic surveys have been done in this area as well. And this is an example of one of our points from our observations. So kind of breaking down, these are just the positions. We use Keck Deimos. So Deimos is the multi-object spectrograph for the Keck 2 telescope. And we use this to get spectroscopy for our members. So we have our primary groups, secondary groups, I'll explain that later. D2 and D3 are the kind of existing spectroscopic surveys from this region. And we have overlapping data from HST and then the Canada French Wide telescope like piece that we so our primary groups are groups that have been detected with X-ray emission, so we can be certain that these are galaxy groups. And overall, kind of the main point of the survey is that we perform spectroscopic follow-up with faint group members or group member candidates around spectroscopically confirmed groups in EGS. So we spent over around 9 days observing these groups. Some of it was done remotely, other parts were done in Hawaii, and this is a video of me in Hawaii. I didn't know that Hawaii had all these amazing concrete skate parks until I came, so it was really good to go and visit on location. Okay, so these are kind of the results from this study. We have a redshift catalog and also some properties of the X-ray selected groups. Overall, we acquire 1,300 reliable spectroscopic redshifts, which we use to determine membership for our groups. And overall, we identify 135 group members, around 11 X-ray selected galaxy groups between 0.66 and 1.02. So again, looking at the results, so this is a color magnitude diagram, and the blue points are kind of the existing data from the D2 and D3 survey. From this, we push to deeper magnitudes, or sorry, fainter objects. And if you look at this in terms of stellar mass, this is kind of the existing galaxies. You can see red galaxies, blue galaxies from D2 and D3. And we fill up this parameter space from our spectroscopic survey. We're able to push you down to much lower stellar masses. Okay, so kind of going to the results, we get 2 cool new points. It's always fun to fill up these parameter spaces. So again, the filled marker is for the more massive galaxies at 10 to 10.5. The unfilled one is for 10 to 9.5. So from the more massive ones, we find that they're actually pretty consistent with results at kind of nearby redshifts. For the less massive ones, we find quenched timescales, environmental quenched timescales that are lower than what was predicted from these photometrically selected members. And the issue with photometry or photometrically selected members is that you could get interlopers, as I mentioned before. And then if you take the redshift evolution of the total pole gap quenched timescale and normalize it by the results at Z0 for the low mass galaxies, you find that it's fairly consistent with the data. Also, if you do it for the high mass region, it's consistent with data. So interpretation is that this more than doubling of the environmental quenching timescale for galaxies between 10 to 9.5, 10 to 10.5 in stellar mass is related to this decrease in quenching efficiency via starvation. That's the main takeaway from this work. We also looked at the dependence between galaxy groups and clusters. This was just showing the slide. The groups are all here. The results from this study, results from previous studies. And these are the clusters. So we just reaffirmed that environmental quenching in galaxy clusters is more efficient than galaxy groups. Okay, so that was the first part of this talk, the bulk of the talk. Now I'm going to talk about some of my ongoing work with students, we're working with, and kind of going through a new direction as well. So this part is part of isolated quenched galaxies. So what does that mean? Why are they important? So this plot here from Get Hot All 2012 shows the fraction of galaxies that are quenched as a function of distance from more massive neighbor. And it's split between the stellar mass of the galaxies you're looking at. And this dwarf galaxy regime kind of mentioned earlier, it's kind of less galaxies that have stellar masses less than 10 to the 9-ish. And what you see is that if you look at the quench fraction further away from a massive galaxy, most of these galaxies are all star forming. Kind of showed that earlier with other plots. This is another way of visualizing this. But we've had these recent observations, discoveries, usually serendipitously, of these isolated quenched galaxies. That you hear Hedgehog and Pearls, SDG, discovered in the JDS2 surveys. And this is just going to just show the distribution of these galaxies fairly isolated in its low mass. It leads to kind of a natural question, I think, is what physical mechanisms quench these low mass isolated galaxies? So this is a question that I had, but I don't have infinite time. So I have a student, Sophia, working on this project using illustrious TNG50, looking for isolated dwarf galaxies that are quenched. And this plot shows the specific star formation rate, which again I showed before, uses an indicator of star forming or quenched as a function of local galaxy density measured in the simulation. So there's 3 different regions I'm going to point out. You have the low density star forming galaxies, you have the high density quenched galaxies, and these low density quenched galaxies. And there's a variety of ways that you can define isolation. In this case, they're using a nearest neighbor approach, and they find a total of 25 isolated quenched dwarf galaxies, and they seem to be fairly isolated if you look at their distribution within the simulation in terms of the gas distribution. So there's key questions that we are interested in answering. The first one being, how the heck did these things quench in isolation? Could it be due to internal mechanisms, star formation activity that blows up the gas in these low mass galaxies, or is it environmental factors? Do these galaxies once reside in overdense region, but were kind of kicked out, and now we're observing them in isolation? So these are questions that my student is currently working on. So stay tuned. You should see some work in the archive in the future. Okay, this last part of the talk relates to this new area of research that I'm going into, which relates to the earliest overdense environments. So this isn't, so this is right here, this beautiful image is the Pandora's cluster, also known as Able 2744. It's a really cool cluster. There's 4 clusters that are kind of coalescing around it. 0.3, right at 0.3. But in the background, lurking in the background of this image, is the ancestor, or softly the ancestor of the massive clusters that we see today. So we can zoom in a little bit. So there's 7 galaxies in this overdensity. This overdensity is 20 times greater than my local volume. And these are the galaxies. This is from Morishita et al. 2023. And these are thought to be protocluster members. Galaxies that are part of a cluster in formation. Now, protoclusters are interesting. It's a region that we haven't really explored. We're able to push to higher redshift now with observatories such as JWST to really explore these regions, but they're difficult to characterize. Before I mentioned that galaxy clusters can be observed due to the X-ray photons that are emitted from the intercluster medium. This is an example of El Gordo. It's a cluster, it's one of the most massive clusters. You can see the X-ray emission. You can also see clusters due to the Sunyaev-Zeldovich effect. You can see B photons interacting with electrons in the intercluster medium. And these are ways that we find clusters. But galaxy clusters lack this. The ICM hasn't developed yet. So protoclusters are awesome. They're interesting, and this frontier that we're still exploring, but they're very difficult to find. As a result, you can imagine the current samples are fairly small. So this is a plot that I put together of the cumulative number of discoveries as a function of time of all the spectroscopically confirmed protocluster members. You can see that we've been growing, but we're really only around 60-ish spectroscopically confirmed protoclusters to date. However, the future is bright with current and new facilities such as Euclid and the Nancy Grace Roman Space Telescope. This number is thought to increase by over an order of magnitude in terms of the number of spectroscopically confirmed protoclusters. But for now, we're limited to the small sample size. And of all the ones that have been discovered before, there's this non-uniform selection function. So some galaxies, overdensities, are found by looking at Lyman break galaxies. Other ones are looking at Lyman alpha emitters, H alpha emitters using narrowband spectroscopy, photometry. Other galaxies look for really dusty galaxies that are thought to be found in very overdense regions at high redshift, such as dusty dwarf galaxies, submillimeter galaxies, and also high redshift radio galaxies and quasars. So these are all thought to trace overdensity at higher times, and these current samples that we have are based on this kind of hodgepodge of different galaxies. But with these future facilities, we should be able to get these uniform selective galaxy protoclusters. But for now, we can use simulations to either better understand our current samples and make predictions for what we will likely see in the future. So I'm using this new spin-off of the TNG 300 simulation, known as TNG cluster. What's great about this, it has over an order of magnitude massive clusters defined with halo masses greater than 10 to the 15 compared to TNG 300. And you get a lot of amazing real looking clusters. So one cool thing about Gaussian protoclusters is they're highly extended. So this is an example of a cluster observed at 0, It's one of the most massive clusters in the simulation. And all the green ones are the cluster members at 0. But as you go back in time, this case at 0.1 and then 0.4, you see that it gets harder and harder to actually find structure and define what the protocluster is. But within the simulation, we can track which galaxy members will become members of the cluster at 0. So one thing you can look at is kind of this effective radius of the cluster, the protocluster over time. So this is in angular units going from 0 to 0.5. And I have 3 bends here. One's a coma-like, Virgo-like, Fornax-like, with coma being the most massive cluster. And you see that this effective radius, which I called R90, it's the radius in which the stellar mass enclosed of all the members, it's 90% of the total stellar mass. And the kind of cool thing here is from an observational perspective is that if you want to find the progenitors of the most massive clusters today, you can just use different radii, different annuli. But you can also look at R10, which is similar. It's the radius that encloses 10% of the total stellar mass. You can think of this as the core of the protoclusters, and you can compare this to the regions that are defining observed protoclusters. And you look at that here. So some of these observations, you can see that they're really only exploring the tip of the iceberg of what the protocluster is, usually the most dense region of the protocluster. So right now I'm doing some studies of looking at differences between the core and the infall region. So you can define galaxies that are in the core, it's 10% R10, and compare it with the properties of galaxies in the infall regions. So this is all ongoing research. This is some preliminary data looking at the stellar mass distribution as a function of distance from the core and star formation rate. There seems to be different populations, so what we're observing could be potentially biased. So this is kind of one of the reasons we're doing this study, to explore these systematic biases in observational data, and also to provide predictive insights into protocluster populations for next generation wide field observatories. But that was a lot, and thank you all again for your time and your attention. I have a few key takeaways, and I will open the floor to questions. Thank you.
Earlier when you're talking about the galaxy group selection on the field, what morphology markers are you looking for to confirm that they're clusters versus just other X-ray images?
So for the groups or the, so the question is for galaxy groups, how can you determine if what you're looking at?
Right, yeah.
Yeah, I mean, some of that depends on the strength of the X-ray emission that you're looking at. Also, you can look at the overdensity itself. So, yeah. Yes.
Maybe this is, thank you very much for the talk. I think it was very cool and clear, and also the visuals were amazing. I have one maybe very naive question. Where do you draw the line between something being a group and being a cluster? Is it the mass, number of members, X-ray gas?
Yeah, that's a wonderful question. The question is, how do you determine what's a group, what's a cluster? In the literature, the typical distinction is in terms of mass. So clusters are thought to be systems that have a total mass greater than 10 to the 14. Or as groups are between 10 to the 12. 10 to the 14. But that is, you know, something that's still in the literature is okay, where do you draw this distinction? But you find, if you just look at the number density of these things, you find way more things that would be in the group range versus like a cluster range. So that's kind of the reasoning behind, rationale behind using this halo mass distinction. Yes.
Isolated quenched dwarfs are rare. How rare are they?
That's actually still an open question.
Okay, you
Yeah,
don't know really,
yeah.
okay.
Maybe with LSSD, once we start getting these faint galaxies, we can start get better constraints on what
Mhm.
the number density should be. Yes.
Correct me if I'm wrong, but. Again, yes, thank you, great talk, it was really awesome. For cluster environments, isn't AGN activity usually what keeps the inter-cluster medium hot so that gas can't fall back down so then we end up seeing, you know, galaxies run out of their own star and they can't get more from, right?
Yeah, from the intergalactic, there's no
Right, so-
cosmological accretion.
So that like is very much in line with everything that you're showing here, right? Where like field galaxies, you know, starvation would be less prevalent, right? Because there's nothing
Preventing the gas from cooling down.
Is that one of the reasons why we might think that in terms for groups, why it's also not as why starvation is the lesser dominant quenching mechanism for groups rather than clusters? Because if I recall correctly, we find more AGN and more obscured AGN in cluster environments than we do in groups and in the field, right?
Right.
So like, do you have a sense of for group environments, how that might what fraction of group members have AGN as compared to clusters or like how much gas could be contained in a group? Like the ratios, like do they scale the same and just there's less gas in groups?
Yeah, so these are all wonderful questions. And to reiterate, the question is, in galaxy clusters, I mentioned they have this intercluster medium, this 10 to the 17 Kelvin gas. It gets heated up about what falls in, but it's sustained, the temperature is sustained due to AGN activity. In groups, you would think, well, groups have lower temperature intergroup mediums. And how does this all relate to what you need in groups? So that's something that I think should be explored, right? Looking at the ratios of AGN and group versus clusters and understanding all the questions that you are asking are questions that needs to be done. I don't have the answers to it. Yes.
Maybe it's another quick question. And in the results that you were showing for the last case, so when you were showing the quench fraction as a function of, say, redshift, for example, so the green dots. How did you so what were the uncertainties that you were plotting? Because then when you go to the quench time, the uncertainties that you get are like much bigger.
Right. So the uncertainties from the quenched timescales are coming from the MCMC
Okay.
Bayesian analysis, right? So it's the 1 sigma uncertainty on the parameters that you get. For the quench fraction, it's the uncertainty on the measurement itself.
I'm sorry.
On the measurement of the quench fraction itself.
Okay.
The observation that is. But that's folded into like the Bayesian analysis as well.
Yeah.
Yes.
That's a good question. So the work that your students doing with the isolated dwarfs, are you just like take a spectra and see like you can find some kind of velocity that you could assume like, hey, this thing's moving very fast, maybe if it escaped some local group it was in, like, do you have any sense or can you tell us like how you go about even thinking about how you?
So for in the
Andrew?
simulation, in the simulations, which is great, you can actually trace their history, like where they were with time. So, you know, observationally, you might want to do something like the velocity, but with the simulation, you can say, okay, if you look back to 4 billion years in the past, where was this galaxy? The simulation, was it an overdense region? And that's kind of the beauty of doing it that way. But we are looking into like doing this, writing like proposals, observation or telescope type proposals to look for more of these isolated quenched dwarf galaxies, just more kind of with, like I said before, a lot of them are found kind of serendipitously, but actually if you look for them intentionally, how many will we find?
Thank you so much.